Hi guys, I'm back. Thought I'd do a little special video here to answer some questions, clarify a few things and stuff, and just kind of, if we got enough time, maybe talk about some other stuff. I got someone who wrote me and wanted me to kind of explain a little bit about rectifiers and how they work. Well, I drew out a basic power supply with a tube rectifier in it. It could be any one of the 5-volt tube rectifiers, directly heated cathode. In other words, it's just got a filament, a couple plates, so it's a full wave. RL over here just makes up for the load that the radio or TV or whatever this is hooked to would be loading it. Anyway, I'm going to talk about what's going on here, and then we'll talk about how the tube actually does it. So basically, over here this will plug into your line, your wall outlet. You turn the switch on and power will come through here. Current AC will start flowing and will induce different voltages or currents in the secondaries. Now we have a 5-volt secondary here that feeds the rectifier tube. We got our high voltage or high tension secondary here. That'll be for our B+. And then down here we'll have our generally 6.3 volt secondary here for the rest of the tubes, heaters. So we end up getting, as the signal comes through, the AC comes through, we get it rectified. It flows out here, charges up the capacitors. We have a choke here. It could be the field coil on an electrodynamic speaker, or it could be a separate choke that the manufacturer decided to put in, or you could have just a resistor here. Either way, this makes up your filter. This is normal pi filter, and then that feeds out pretty much DC out. There'll be a little ripple, but not much, not enough to hurt anything, to the rest of the radio. So let's look at some things here. We're going to look mainly at this. This is where our B+ is going to come from, is right here. Now at some point in time, we're going to have a signal, AC, coming in here, and at some point it's going to induce it, and we pick up instant in time. It'll be positive here and negative here. Now since this is a center tap for the return path on the ground, we'll have negative, positive. Both show up there. So with a rectifier tube, when the plate is positive, one of the plates, if they're positive, we have current flow. If they're negative, we do not. Now the heater here, or the filament, this is called a directly heated cathode, meaning that the filament itself is the cathode as well. It heats up, it produces electrons. So if we have positive up here, then this plate is positive. This down here is negative, so this plate's negative. This one will not conduct. I got electrons here, I got a negative charge here, and I have a negative charge showing up on this bottom plate. You cannot get conduction. Like charges repel each other. But here, I'm going to have a positive charge down here, and this is already negative. They're producing electrons, bunches of them. So when this is positive, then we get a current flow, because unlike charges attract each other. So there'll be a current flow through here. Now if you follow the idea of electron flow, which means negative to positive, then the current flow will flow through here, up through, down through the ground. All the grounds are connected, so it'll go through here to charge up the caps, and then come to the radio, feed the load, come back, and back here. All this 5 volt secondary is doing is just applying the heat, supplying the current to produce the heat, to heat that up. Otherwise, it doesn't do anything else. So if we go from negative to positive, then we'll flow this way. We come here, we follow out the ground, follow through the load, which is our radio or TV, feeding all those tubes, coming back through and back to this point. If you follow the standard, or what they call positive flow, or positive to negative, or conventional flow, then it's just the reverse. We follow through here, current flows through, goes through this way, through, back through the radio, back around to the return path, and back. Now, so how's rectification taking place in this tube? Well, it's taking place because in any rectifier tube, we have a cathode. Now, it'd be directly heated or indirectly heated. It doesn't matter. But that cathode, when it's heated up, starts boiling off electrons. So I have a bunch of negative charge here. So that's negative. We get rectification when one or the other plate. Now, they do make tubes that are just single diode rectifiers, half wave. This tube has 2 plates, so when one of the plates are positive, then you get a current flow. The other plate here, in this instance, is negative. And negative to negative repels each other, so there will not be nothing flowing through here. Now, so this basically is at the time we got the AC here, it's at this point here anytime in this part of the curve. So that's what's flowing on this part. Now, at some other point in time, this is going to change. And this will be negative, which will be negative here. This will be positive. This will be positive. And at that point, we're in this part of the curve. And what comes out here, though, will look something like this. Before it ever gets to the filters, the first part of the wave, then this part of the wave is next, and so on. This part's going to conduct because at this point now, down here, this is positive and this is negative. So with this positive, we get conduction. Can't get conduction here because it's blocked. And these would be the same height. Now, at some point, I want to do a little more in-depth video on power supplies themselves, mainly because no one's asked it yet, but I want to explain a little bit about the filtering circuit and what you're going to see here in voltage and stuff. But I'm not going to do it in this video. It'll be getting kind of long on that. So that's basically what's happening in the circuit. Now let's just look at the tube itself. So we'll get rid of all this and we'll look at the tube and try to understand it a little better. So we have this tube, and it can be any one. I'm just drawing a full wave one. So with the directly heated, so it's going to be kind of working around the camera here, tripod. It's going to be one of the 5 volt, so it's going to be a 5XX tube. Be 5U4, 5Y3, 5Y4, 5V4, 5Z3, 5Z4, and so on. There's several of them. So that's what we're going to be talking about. Basically, the 5 just means that we supply 5 volts to the filament. And the rest, the letters, it just in factory or in company letters, and then these numbers kind of talk about the active pins and stuff. This is also known as a diode, or actually this one would be a double diode in the strictest sense. Diode tube can be a rectifier tube or a detector tube, but diode, the name diode is di, for 2. Ode is just a shorting of the electrode for electrode. So 2 electrodes. And the more honest way of saying it, 2 active electrodes. So we have 2 diodes in here because we got 2 plates. But if we just looked at one side, it's just a diode. Here we got 2 active units. The cathode and the plate or anode. If you got a triode, well then you've got a cathode, an anode, and a grid. 3 active elements. If they're indirectly heated cathodes, in other words where there's a separate metal tube for the cathode and the filament then becomes just a heater that heats up that, then we don't count the filament at all, or the heater in those, because it's not active at that point. But in a directly heated, it is the cathode. So what goes on in here, basically I supply 5 volts to this. This thing heats up, lights up, just like a light bulb. So you're supplying 5 volts there, a certain amount of current. You know, depending on what they are, a 5U4 would be 3 amps for this little guy. So that's 15 watts. 5Y3, 5Y4 is 2 amps, 10 watts. But it heats up. When it starts heating up, we get electrons bleeding off of here. Just boiling off actual individual electrons. Now, if there's no power supplied to these plates, either one of them, nothing happens. They'll just stay there. They'll build up to a certain amount of charge, a certain number of them, and then they stop. Nothing else goes on because electrons don't like each other. So, like charges repel. I can only build up a large enough, a certain size field of electrons here, and then it stops. The minute either one of these 2 plates get a positive on it, supply positive current to it or positive charge to it, these guys will head to that plate. If this one, in a full wave rectifier, when this one's positive, this one will be negative. They will not go there because this has got a negative charge. I'll draw it with like a circle around it. This has got a positive charge. We'll draw the charges with a circle. So they just go up and turn back around. They may even go up and just head over here. And you get current flow. Now if we change this and make this positive, and get rid of that in there and make that negative, then everything changes. Now they'll flow over to here. Any of them over this way may see that and then turn, may go this way, may turn back, but they're not going to go up there. So now I got the current flow here. And this is going to switch back and forth, several times a second. I mean, you got 60 hertz. 60 hertz is 1 full wave. So it switches 120 times per second, back and forth. That's it. That's how it works. It's just the fact that I heat this wire up, and that wire will then start energizing, putting enough energy due to heat into the atoms in it that some of the electrons will fly off. They'll come off of the wire. The general standard term is calling it boiling off electrons. And they'll boil off. They'll come off the wire and they'll be out in space here in this vacuum until I put something on these plates. As long as it's a positive charge there, then they'll go right towards that plate. That creates a current flow, then goes on and flows through the circuit. They'll actually flow this direction. So your current will be flowing through here and back around. But that's it. That's how it works. Now the reason why they don't call a rectifier tube a diode tube, because they want to keep a distinguishment between a detector diode tube, such as a 6H6, a 5L, a 6AL5, or some of the others that are a combination, like a 6Q7 or 6SQ7, 6AV6, 6AT6, which have triodes and dual diodes in them. These are all for detectors. Very low current. They would never handle the current that virtually any rectifier tube is dealing with. But they work just fine as the detector. It's extremely low current, generally low voltage, so they work fine there. Whereas a rectifier tube, even though it's an actual diode tube, and it may be a single diode or a dual diode, which means either it's a full wave or half wave rectifier, they handle very large amounts of current. Some of these, like the 5U4, can handle really large currents and very high voltages. And we're using them to actually rectify, so the idea was just give it the name rectifier tube, and that distinguishes it between it and just your standard detector diode or just diode tube. So hopefully I think I explained it good enough for you. Now as far as what's coming out of here, it will be DC, but it's extremely rippled. You're going to see, like I showed before, a DC signal looking like this until you go through the filter. Then the filter will smooth this out and fill in these gaps so you get more just a straight DC. Now it'll probably still have a little ripple on it, depending on how much filterization we do. You know, some companies and some sets, radios or TVs, sometimes put in a dual pi circuit, meaning that there'd be one capacitor, then a choke, and then another capacitor, and then another choke, and then another capacitor, to really smooth it out. But for all practical purposes, it's pretty smooth DC. So I hope that explained it. If you have any more questions, just contact me or send me another message or something, and I will try to answer them to the best of my ability. Okay, now what we're going to talk about. Well, a while back, Art contacted me and asked me about why they use capacitors and sometimes resistors when doing alignment, and he talked about dummy antennas and stuff, and I misunderstood him on the resistors. I thought he was talking about the termination resistors and not the ones that some radios use. And so he's still quite wondering about the resistors a little bit, because the radio he's working on is, okay, just kind of zoom in there, is a broadcast band with several shortwave bands, and on the shortwaves it says that when you're doing alignment, use a resistor. So first we're going to talk about that. We're going to pay attention to the front right here, this circuitry here. I can get this thing kind of adjusted the way I want it, and kind of zoom in a little bit. Just a hair. Okay. Now, this is your antenna connections on the back of the radio. And it says that, well, pretty much all, for the entire alignment except for the IF, you hook to the antenna connection. Only the IF we hook over here on the grid of the, as they call it, the oscillator translator tube. It's mixer tube, converter tube. But that's the only time when you're connecting there is when doing the IF alignment on the radio. Otherwise, everything else, all bands, the oscillator adjustment, RF adjustment, and the mixer adjustment is done connected here. Now in broadcast band, or just your standard AM band, they're using capacitors. Now in this case, I said in my previous video that generally a capacitor is used for blocking, but we don't need it in this case because this thing is feeding down through a transformer here. It also feeds through the switch up to this coil, but there's a cap already here. That isn't in this particular case why they're using the caps. They're using 200 picofarad caps to do the oscillator, the translator, and the antenna or RF. Here in the antenna and stuff. So pretty low value. It produces a decent amount, a reasonable decent amount of capacitive reactance or impedance, and so they're using it more for an impedance device to increase the impedance in this circuit. And why they're doing that is so that it doesn't load the signal generator, RF generator, down. Now once they get out of there, once you got your broadcast done, then they move to the various shortwave bands. It's like B through E. It's got several bands on it, covering several different frequencies. All those are using a 400 ohm resistor. Basically, the main reason is the capacitor, it just become not really good. They need more higher ohmage, so they're going to use a resistor that works better for them. So, and it probably does help to keep the capacitance out there on those higher bands. So they're going to use a resistor. Again, it's to keep from loading the RF generator down. Now, why is that? I mean, I can crank the generator up, can't I? You know, I mean, if this circuitry is not high enough impedance, so it's loading it a little bit, I can just crank. You know, I mean, I've got quite a bit of attenuation adjustment there. I can just start cranking it up, and you could. One thing to remember about RF generators, the output that is fed out there, what is producing that, what it goes through, basically all that's inside there is you've got a oscillator in there that produces your signal, and it's variable, so you know you can get different frequencies, and of course there's different bands. That is sent through another tube to amplify it, but it's more of a buffer. It's a cathode follower, which is less than unity gain. In other words, it really don't have any gain at all. It feeds off the cathode, and that feeds out. Now the reason why they use those is they're very low impedance. When I'm feeding a signal in, the device I'm feeding it into, or that's coming from, needs to be low impedance, and what I'm going to should be high impedance. that gives me the best flow. Being that thing is less than unity gain, we're relying on how strong that oscillator is, how much gain it has, how much power it has. If I start loading it too much, even if I do increase the attenuator, I'm only going to get so far. RF generators only put out so much power. You don't want them putting out a lot of power, otherwise you start interfering with the neighborhood and everything. Then the FCC kind of gets a little upset about that and stuff. And you don't need it. So there's only so much that I can do. When I get to a certain point, and I'm still loading that thing down quite a bit, I might be picking up an output with my output meter a little bit, but what ends up happening, if it's loaded too much, it'll start harmonicking and distorting the signal. And then you gets all kinds of harmonics in it, usually odd harmonics more than even, but it'll really make a mess of that signal coming in and you won't be able to use it. So that's why they use the resistor and in there, is just to keep that from happening. And why are they, changing things? Well, for one thing, we're changing frequencies, but also as we change frequencies, we're reducing the impedance on these coils. To get to higher frequencies, I got to reduce the number of turns on those coils, which reduces the inductance, which reduces the inductive reactance, which is part of the formula, and impedance. So I'm lowering my impedance. It's going down. So I need to keep it up at least a decent level for it to work. It don't have to be like megohms. That's no problem. It just got to be a few hundred ohms just to get things to not load that generator down. So that's the whole reason why they're using resistors in there, and some other companies do. Other companies, the circuit may be designed quite differently on how the antenna feeds in. They don't need to do that. Now, one other little point, and mainly for Art, but anyone else has seen one of these radios. This is it's a Sears and Roebuck or Silvertone 6338, Arthur Hollingsworth's channel. He's been working on this and restoring it and everything, so you can head over there and look at, he's got several videos on it. But an interesting note to make, and it's something that I remember seeing way back when he first started on this, and I totally forgot about saying anything until now. When he was asking a question, I was looking at this, also looking at another problem he had. This RF tube is only in here, it's only doing work, amplifying the signal. It's only working in broadcast band. When they switch out, or when you switch the band switch to band B, C, D, E, this is not in there. It's not doing anything. All the shortwave bands bypass it and go right to the mixer too. And you'll see that in your alignment instructions. It talks about once you get above broadcast band, all it talks about is making adjustments for the oscillator and basically antenna. They're calling it the mixer, but either way you look at it, because once you get out of the broadcast band, this part of the tuning condenser does nothing. This whole circuit here is out. I think I ran out of time for this thing and it shut off. Okay, I don't know where it cut me off at, but as I was saying, when you're in the above broadcast, any of the shortwave bands, this L2 and the tuning condenser here and this tube is not doing anything. It's all out of the circuit by the switches. Down here, this part of the tuning condenser now becomes the antenna tuning, or the bandpass tuning, or the RF tuning, and it works in conjunction with these coils down here. And then, of course, over here, this guy right here is the tuning condenser that is, or part of the tuning condenser for the oscillators, coils. So a little interesting note. Now, the other little problem he's having, and I had to look back on some of your videos and stuff to kind of remind myself what was going on and everything. But he was making an adjustment, doing alignment. And correct me, Art, if I'm wrong in the comments, but I'm pretty sure I didn't go through all the videos, but I thought you had done in the past alignment at least a couple times on this, at least IF a couple times, and it worked then, and now it's not. Okay, oh, one other thing before we get to that, what I want to talk about on that, as far as your C, band C and E, not really seeming to work real good, or at least not your signal generated when you put it on the right frequencies, you're not picking them up through there. Check your wiring. Like someone else said, I don't know, they kind of said maybe you got the two mixed with each other, but which is possible, but I'm thinking more that you might got one of the coils hooked up backwards on them. You know, if you get these kind of flipped, the oscillator will still run, but it'll run at a higher frequency, and it'll only run in a part of the band, part of the tuning condenser. You start moving it more and more, and it'll shut off. It's not running perfect. So just check your wiring on those. I think that's all you're going to find that is going on there. Now back to the IF. That first IF, I know you changed it out to a different one. It's supposed to be 455. You changed it to a 456. 1 kilohertz will easily adjust out. The thing is, what your problem is, it's acting like that this is wanting to resonate at a much lower frequency than 455. Not a higher one, but a lower one. If you remember, or anybody else, as far as that goes, our formula for resonant frequency, yeah, kind of nasty looking F there, is 1 over, we'll have 2 pi here, the square root of L and C. L is your inductor, your coil, and C is your capacitance. Now, I don't have to worry about, oh, that's great. Let me adjust this so you can see what I just wrote. Okay, there we go. Sorry about that. But we don't have to worry about the 2 pi or anything else here, or even the square root. Basically, what you need to understand, and let me back out here just a little bit, is something kind of like this, just a rough thing like this. The big thing is to understand that frequency, the resonant frequency, is inversely proportional to the inductance or the capacitance in that resonant circuit. Meaning, if I hold C steady, in other words, keep the same capacitance and don't change it, but I change the inductor, if I increase the inductance, the frequency drops. If I drop the inductance, the frequency goes up. And the same way with the capacitance. If I keep the inductance same, then, and vary the capacitance, if I increase the capacitance, frequency goes down. If I decrease the capacitance, the frequency goes up. Now you see what's going on with your radio on that IF can. By unscrewing the pattern out, that's decreasing its capacitance. And he said you got it all the way out, and it's still not enough. The screw's completely unscrewed, and it's still not peaking. Well, it means, see, I'm trying to decrease the capacitance to pull the frequency up. The frequency is below 455 for some reason. Well, if it was actually the other way, I would say that, you know, if the frequency is way high, I would actually come back and say, well, maybe the inductor, because that would mean very small inductance, that the coil in there, on that primary coil, might have a shorted between some turns, and it's reduced its inductance. But no, it's acting like the inductance is way high, because the frequency is low. Well, there's no way, naturally, or just normally, you can increase the inductance of a coil. The only way you can do that is add more wire to it. So unless you took that thing apart and had more turns of wire on there, I don't think that happened. So we have to look at the capacitance. what's going on in here. And let's bring this down here so I can kind of zoom in on it. Alright. Bring that up a little bit. Okay. I hope you guys can see this alright. So, this is our guy right here. We basically, the way it's setting right now, we got for some reason we got too much capacitance. I know that in this case, there's nothing can be going on with that inductor. It's the coil is formed on, if you didn't change the IF since when you did change it, then it's coiled onto a wooden dowel. So there's no way it's going to change, you know, other than it's short and go down inductance, but it's acting like it's too high, or we got too much capacitance. So we have to start looking at the circuit capacitance. Well, if we look down this way, say, you know, something got, you know, I don't know, I know you took some of the coils out and redid them, put them back in place. I don't know if you did both L3 and L4 when you pulled all that apart. Well, it does connect over to L3. The only problem I've got with this is if there is something going on here in the connections or something, I would think it would also affect T2 as well. Because anything below these, on this side of the primaries, any increase in capacitance due to something going on, circuit capacitance is what I'm talking about, would not only affect this one, it should be affecting this one as well. But, you know, never say never either. So you might want to check and make sure, if you did pull L3 out, make sure that all these connections are correct and their correct placement. Okay? Now, the other route would be the tube, because it directly connects to the plate. There's nothing else there. Now, I will tell you, if a tube starts going gassy, it's not gassy enough to really be noticeable, you know, or to harm the heater in there and burn it out or anything like that. But if it's starting to go gassy, the internal capacitance in the tube will start increasing. Basically, it's because you're changing the dielectric constant that's in there. A brand new tube or a good tube has a vacuum. Once I start putting gas in there, though, it starts, you know, losing its vacuum. Then now I'm getting air in there, and that changes that dielectric constant. And when it does, the capacitance goes up. There's a possibility that that tube itself is what's causing this. Now, how do you check it? Well, that depends on your tube tester that you got. If you got a good enough tube tester that does gas tests and it's working correctly, you might be able to measure it. You can also check it for shorts. The one thing I would do when you are testing that tube, if you decide to test it, and that's a simple thing because you just unplug it, you know, pop it out, pop it in the tube tester. Leave it in there. Don't just let it get warmed up enough just to test it. Leave it in there for 20 minutes. Let that thing heat up good and see what it's doing. See if it's, you know, when it's kind of cooler, when it just got warm up enough to show some emission and actually start current flowing through it, it may not actually check bad. It may have to take time before some of those problems may show up. So let it heat up a good 20 minutes or so to see then if it's okay. The other thing you can do is you can plug the tube back in, and when it's cooled back down, pop the grid cap off, hook your meter to it, your digital multimeter or your VTVM, down on the lowest scale, hook to the grid, measure to ground, okay, with no grid cap hooked on, no wire hooked here. What that does is now the grid is getting, it's seeing a 10 megohm resistor in circuit, because that's what your meter's doing. It's 10 megohm impedance, 10 or 11 So it's like a 11 megohm resistor connected from the grid to ground. Now, what you're looking for, you power it up. Now I've actually never done this on a mixer tube. I've done it on IF tubes. I've done it on a lot of other tubes where the grid is actually right up next to the cathode. Mixer tube, the control grid actually sets a little ways away from the cathode. So I'm not sure what you may get there. There are some positive plate or grids around that's got a pretty decent positive voltage on them. So it may want to contact to positive, become more positive than negative. But in any case, it's going to start, once the tube starts conducting, it's going to show some voltage on there. When it does while it's cold, take note of that voltage. Now as it warms up a little bit for the next minute or two, it'll probably fluctuate, may increase just a little bit. That's okay. But now let her warm up. Let her get, 10, 20 minutes, 30 minutes. If this thing starts creeping up, as the warmer that tube gets, the longer it's on, then there is a secondary emission, and it's usually caused by gas in the tube. So the grid's leaking, basically, is what's happening. And if that's the case, then that tube has got some gas in it, even if you don't have a way of measuring it. And thus has higher capacitance, which is throwing off that circuit capacitance on the IF. Now, assume that you do all this and you can't find any fault with the tube, or you've got a new old stock tube, or you got another tube out of another radio that you know is good, it's working, it's everything, and you put in there. What else can be? Well, on those patterns, one other thing that can happen to them, and you've seen them, you've looked at them, you've had those IFs apart. Let me zoom out here just a little bit. But basically, you got this one plate, it comes down, it may have a connection, a little deal here bent. That's the bottom plate. It may tag in right here on that porcelain, and this comes down, and it'll hook to the wiring here and the coils and stuff, and the outgoing wire. Then there'll be a sheet of mica, and then there'll be another plate. Generally it comes in like this and comes across, and it'll just be flat. There won't be nothing connecting down here. And it goes, hooks up to your stuff. And then you got your screw, coming down through here like that. Alright. The head will be down here. There'll be a washer on there for insulation. What happens when the screw's down tight, this sandwich is pressed tight together. As you start unscrewing it, this springs. This is kind of springy steel material, and it'll start springing up. So it'll start moving up like this, following that screw. And it should follow it all the way until you get it, when you fully unthread it, and it actually should have enough that actually it'll pop the screw completely out. At least out of the hole a little bit. I have seen these where this, for some odd reason, for various reasons, has lost some of the springiness or doesn't follow the screw all the way. What happens is when you start unscrewing it, the plate will fall a little ways and then it just stops. And if you're actually watching the meter as you're doing that, you'll see the meter, moving as the screw is moving. The plate's opening up, the capacitance is going down, but then it just kind of folders. It doesn't move much more. There may be a slight little twinging there a little bit, because as the screw continues outward, it may catch that plate a little bit or something. But it basically stops. And you keep unscrewing. If you take the can apart, you'll find it kind of looking like this, where the insulator may be laying on top of the plate. The screw will be way out and the plate will be down a ways. If that's the case, what's happening is it's just that you're not getting the capacitance adjusted enough. because it can't. The plate can't open there far enough. What you can do is pull the screw out completely and lift this plate up a little bit, gently try to get it bent up some and see if that'll work. A lot of times it will. You can just kind of bend it up a little ways where the screw's now going to contact it when it's totally unscrewed. Go ahead and screw it back down and then release it again and see if it stays true. If it stays true, it's good. You do, I believe, still have the old parts of the old one that was in there. They appeared to be, those patterns appeared to be about the same size plates. So if you have to, you could always, if this one just will not work right, now that's what's wrong with it, you could remove just that plate and put one of them in there to fix it. That's another problem that can be something of that nature. Don't know if it is, but it could be. Otherwise, some other circuit capacitance is acting up in here, because there's really not much else that can go wrong. Again, like I said, it's acting like, it's basically saying that it's resonating at a much lower frequency, or a lower frequency in 455, because you're trying to reduce the capacitance to shove the frequency up. The other thing you could do is kind of screw that down a little bit, at least get the threads making contact again, and then leave your, hook everything up like you're going to try doing your alignment again. And when you know that transformer is not going to work for you, well, and it'd be better if you could move your meter closer to it instead of where it's at. I'm not sure. I didn't read the instructions. I don't know if they're pulling you off where they're pulling the meter readings at. But move it a little closer. What you could do then at that point, watch that meter and crank your generator down in frequency until you see the meter peak out. It'll go up so far, and then it'll start going down again, so you move the generator back and see what frequency it is. It'll be kind of curious to see where this thing wants to resonate at. And that'll kind of give some idea what the problems may be, what's going on for sure. But check the tube, as I said, check that in there. Do that as a last resort thing, because the other thing you could do, just to make sure that there isn't a double image, usually on IFs there isn't. You may see this in some of the oscillator coils adjustments down in here, could have an image where you get a double peak. Usually IFs with capacitors don't. But just to make darn sure it doesn't, you could crank that down before you start turning anything apart or anything else. Crank it all the way down, tighten her up, give her the maximum capacitance, so snug her up good, put everything back, the generator on and your meter on, and then slowly start taking out. The other thing that's going to show is if it doesn't peak, what it's going to show is let us know as that meter moves up, if there's a certain point as you're screwing, it kind of just stops, and you keep unscrewing, the screw keeps unscrewing and it doesn't do much more, then it's probably that plate problem that I was talking about earlier. But it could be that you started out at a point where this thing just, you're trying to hit the second peak. So you might just try that also as a thing. See if you can find a peak down there. So, but do the simple things first, like the tube, screwing that screw all the way in, and watching the meter, checking the tube out and doing those tests and stuff. Those are the simple things. It doesn't require breaking up the soldering iron or anything, or any tools other than the generator and tube tester and the meter. So, at that point, I really don't have much more to say. The other thing is you could just make sure this wiring, I do believe that C&E is just because maybe you got a couple of coils flipped, the wiring on them. So you might check that and double check it. The other thing too is you could pull your scope out and hook onto well, it'll be the grid here on the oscillator, and see what they're doing. You know, those particular bands, see what, and you can kind of get an idea what frequency they are actually running, and if they will cover clear across as you rotate the dial through, or if it stops oscillating. So anyway, check your wiring, check that, and see what you can kind of come up with this IF. So that's about all I got. I don't really have much else, so if you like the video and stuff, you know the drill. Give it a thumbs up, and you know, comment, like, share, things of that nature. And thanks to my new subscribers and everything, and I hope I answered at least these 2 questions and good enough, and let me know if I did. So I guess I'll see you guys on the next video, and thanks for watching.